want to start? I'll get the appropriate slides up of who knows. So, yes.
What is the, I understand like the 11-year sunspot cycle, but what's a 22-year magnetic cycle?
Yeah, 11-year sunspot cycle, 22-year magnetic cycle. You know what? It would be good if I get through all the slides for that. So, but in a nutshell, yeah, that's my lovely wife and I. That's a trick-or-treat trail today with my UC 160 class. Thank you for sharing that with everyone. Anyway, that's why I'm kind of frazzled and running around all day.
Where was the trick-or-treat trail at?
Deer Haven Park.
Okay, I intern with preservation parks, so I'd like to.
Oh, really? Oh, yeah. So they had this big, and then last year they had 700 people, so they kept it there. Sure, we had more than 1,100 people.
Oh my gosh.
So yeah, it was
Great
crazy.
turnout.
Yes. And
Where's it at?
a couple miles.
It's on Liberty Road, right?
Yeah, south of campus on Liberty Road.
No, like where in the park?
Oh, at the back.
Like the,
Like in other words, there's soccer fields in the front. You keep driving, and
like nature center.
yeah, by the nature center. Yep, there's a trail back there. So you give out candy to kiddos, and it's fun. And let me find this here. Here we go. Okay, courses. Astronomy 111. And it's a long time. Yeah, I've been doing this a long time. 2017 fall. First was like 2000. Were you born? Yeah, I guess. Borderline. Actually, the first time I thought this was 1990. To your shared with students. I'll get it here eventually. I might as well bring this one up. And then we'll bring up chapter 14, ASTR. And then we'll bring up chapter 15, surveying the stars. Chapter 14, ASTR, magnetic cycle versus sunspot cycle. So the sunspot cycle is just the up and down variation in the number of sunspots, whereas the other piece of that is there's a 22-year cycle, two 11-year cycles for one 22-year cycle because, excuse me, the orientation of the sun's magnetic field flips with every sunspot cycle. So in any given sunspot cycle, there's a pattern in the magnetic fields of pairs of sunspots in the northern geographic hemisphere of the sun versus the southern geographic hemisphere of the sun. So for example, during one sunspot cycle, you might have a situation like this, where when you have pairs of sunspots, it looks a lot like there's a horseshoe magnet under the sun. Of course there's not, but the magnetic field looks a lot like that, where there are these arches of magnetic field lines that connect the two sunspots. And so magnetic poles come in pairs, a north pole and a south pole. So in one magnetic, in one sunspot cycle, you can have it where the sunspot group that is out in front in the direction of the sun's rotation. The sun rotates with the north pole up, the sun rotates from left to right, so to speak, from west to east, just like the Earth does. So notice there's a pattern here where the south magnetic pole of each sunspot pair is out in front in the direction of rotation. The north one is in the back in the northern half of the sun, but in the southern half of the sun it's flipped around, where north magnetic polarity is out in front in the direction of the rotation, and south magnetic polarity is trailing. The next sunspot cycle, those would be flipped. It would be that in the northern hemisphere, north magnetic polarity was out in front, and in the southern hemisphere, south magnetic polarity was out in front. So the sun's overall magnetic field flips from one sunspot cycle to the next. This is illustrating this overall idea here, where here's one sunspot cycle where the magnetic field lines point out of the north geographic pole of the sun into the south geographic pole of the sun. And the convention with magnetic fields is that makes this as a north magnetic pole, and this is a south magnetic pole. But when you get to the next solar minimum, starting the next cycle, notice that the sun's north pole, geographically speaking, rotationally speaking, has become a south magnetic pole, and vice versa. So the sun's overall magnetic polarity flips once every sunspot cycle. So it's kind of like saying, then, suppose I have a coin and it says heads right now, and if I flip it over, what's it say? Tails. And I flip it over again, it's back to heads. So I have to go through 2 sunspot cycles to get back to the same magnetic field configuration. I have to flip the flip, so to speak. So there's a 22-year magnetic cycle because you have to go through 2 11-year sunspot cycles to get back to the same original magnetic field configuration. And that's why there's that difference between them.
How are we able to know that's occurring?
Because we are able to, well, so certainly, you mean like, how do we know the magnetic field is flipped like that? Is that what you mean? Like, how do we know the magnetic field?
It's back to what it was.
Yeah, so it's because we're actually able to measure the sun's magnetic field. And I'm trying to see if I don't know if I included an indication of that here, but there's a type of specialized, there's a type of specialized photograph that you can take that utilizes what are called circularly polarized spectral lines, and circularly polarized light from spectral lines, and those are sensitive to the direction of the magnetic field is what it comes down to. So we are able to make what are called magnetograms that tell us the direction of the sun's magnetic field, and it's using that tells us that it flips with every sunspot cycle. Next sunspot cycle, it flips around compared to the one before that.
Could you go through what you were doing at the end of the last class about when during the eclipse when the moon is behind and when it's in front?
So first of all, is there any questions about the, so I'll get to it. Is there any questions about the sunspot cycle versus magnetic cycle question? Yeah.
So, what distinguishes it is the fact that it's going to flip every 11 years.
Right. The number of sunspots rises and falls every 11 years. Actually, it varies a little bit at how much time it is. But on average, it's about every 11 years. This is a plot of sunspot number versus, well, percentage of the sun's surface covered by spots versus time. So the more spots there are, the bigger percentage there is. So here's a solar maximum, here's a solar maximum, here's a solar maximum. Those are separated on average by about 11 years. If we look at the sun's magnetic configuration for this maximum and look at it for this maximum, it's opposite. The overall solar magnetic field direction, which rotation pole of the sun is the north magnetic pole, which one is the south magnetic pole, will have flipped from this solar maximum to this solar maximum, actually for this entire sunspot cycle, So when we go to the next one after that, it flips the flip. It's back to what it started with, kind of like flipping a coin twice. So therefore, 22 years later is when you're back to the configuration that was the one that you were starting with. Yes?
Realistically, what effect does that have on, like, I guess, on sunspot?
It doesn't have any effect on like what the sunspots look like. We can measure their magnetic fields with a magnetogram and see that it is flipped between them, but it doesn't look any different overall. You couldn't just look at white light, ordinary light photographs of the sun and tell the difference as far as that's concerned. But the flipping is associated with the generation of the sun's magnetic field is what it comes into. That's giving us an important clue about, about why the sun is magnetic in the first place. That's what that comes down to. So there's a question about eclipses with the sun in, like the sun in front versus the moon in front and all that sort of thing. So I will tell you that we name eclipses after which body is being blocked. So in other words, at a solar eclipse, it's the sun that's being blocked. In a lunar eclipse, it's the moon that's being blocked. It's falling into Earth's shadow. But I'll also tell you that eclipses are not on the upcoming exam. So that's not something that we should probably cover in any detail right now. That's actually more of an Astronomy 110 topic, but excuse me, I talked about it in here because we just had solar, so we were talking about the sun, and I'm all choked up about it. Just a second, I'm giving somebody else a chance to raise their hand. Yes,
I think the question was about binary.
Oh, eclipsing binaries, I see. Never mind, okay. Yes, that could definitely show up on the exam. Right, yes, eclipsing binaries, sorry, okay. I misinterpreted. Yeah, there could definitely be eclipsing binaries on there. So you're talking about, like when we were doing the lecture tutorials. And we were talking about when one's in front versus the other's in front, what effect that does that have? Yeah, let me pull it up because I have the lecture tutorials. I scanned them into PDFs here, so I can bring that up and talk about it. So, where am I? Get my back in front. So let's see, that one should be a binary star, it should be called. Yeah, this one right here. Okay. Right, so the question is basically, what that's related to is, here's the light curve. Here's how the overall brightness changes with time. And we've got two stars. And for example, we could have, let's look at it. Started with like a G and an A star. Later on though, let me talk about, I think, because they were asking you to figure out. Imagine that you're watching a binary star system containing an M spectral type main sequence star and a B spectral type main sequence stars. They complete one full rotation. So let's just kind of draw that. I think I even have some colored chalk here. Cheating because you can't draw that with colored chalk, but whatever. All right. So a B-type star, what color is it going to be? It's going to be blue because it's hot, right? So the B-type star is going to be blue. And on the main sequence, remember that as you go up the main sequence towards O and B and so forth, the stars are getting bigger in radius. So if you're off the main sequence, then all bets are off. There's no tight correlation between spectral type and size off the main sequence. But on the main sequence, O and B are the largest main sequence stars, K and M are the smallest main sequence stars. So the O star is going to be blue. What color is the M star going to be? Red, because it's a cool star. So I am going to draw a big blue star. Oh, such artistry. And a small reddish star there. Actually, the red star would be much smaller than that compared to the blue star, but I don't want to make it too small for you to see it really. Okay? And then these guys are orbiting their common center of mass, passing in front of one another. So one situation that will happen as they orbit one another is that at some point, the red star is going to be in front of the blue star. So that situation would look something like this. Here's the red star sitting in front of the blue star. So blue star partly covered by the red star. And then that's one of the types of eclipses. What will it look like in the other type of eclipse? You only see the blue star because the red star goes behind it, right? So at some other point, you'll only see the blue star. So this is going to be a situation where see them both. And here, red, this is terrible chalk, red in front of blue, here, blue in front of red. And so our task is, well, the task in the lecture tutorial is draw the light curve. Well, guess what? When you draw the light curve, you're going to sketch something that looks basically like this. And then the question is, which of those configurations corresponds to various parts of the light curve? So when we have up here, this is when the maximum brightness is what we're seeing. It's as bright as we see it. Is that going to be, I see them both, red in front of blue, or I only see the blue star? Everybody at once. Both. Yeah, when you can see them both, you're getting the most light. So any point where it's the maximum brightness, those are, see them both times. You can see both of the stars. So when one star passes in front of the other star, you got an eclipse, light is being blocked. Light's being removed because one star is blocking at least part of the other star. And the question is, when do I get the deeper eclipse? When does more light go away versus when do I get the shallower eclipse? This is primary eclipse when more light goes away. Secondary eclipse when less light goes away. When will I see primary, deeper eclipse, darker overall? When will I see secondary eclipse? I lose some light but not as much light. So let me ask you this. If I got a red star and I got a blue star, if I look at each square meter of those star surfaces, which one is sending out more power, more energy per unit time out of each square meter of its surface? The hot star or the cool star? The hot star does, right? The hot star does. So when am I going to be getting rid of more light? When I'm blocking the hot star or when I'm blocking the cool star? Blocking the hot star. So the deeper eclipse is always when the hot star is behind. It's always. It doesn't matter which star is bigger and which star is smaller. All that matters is when the hot star is behind, that's when you get the deeper eclipse. Because the thing to notice here, and I do want you to be able to explain this, the thing to notice here is in either case you're covering up a smaller star-sized area. Here, I'm blocking the whole smaller star, so I'm covering the smaller star's area. Here, the smaller star is covering a smaller star-sized chunk of the hotter star's area. So I'm blocking the same amount of area in both cases. I want to write that down with a piece of chalk that is not that one. Okay, so the same amount of area is blocked during both types of eclipses. But, all right, I'm going to go, I need more room because I'm not writing over there because the camera is only showing this part. This is what it comes down to. So I'm going to erase this here. Just burn it into your, you've got this burned into your memory there. Okay, I'm going to erase that there. But the hotter star emits more light per unit area. Therefore, blocking the hotter star removes more light. So that's the deeper eclipse. And again, it doesn't matter which star is bigger, which star is smaller. It wouldn't matter if it was the red star that was big and the blue star that was small. All that matters is blocking hot star area is more effective at removing light than blocking cool star areas, because it's the same amount of area that gets blocked during either kind of eclipse. So in other words, this right here, red star in front, blue star behind, that'll be the deeper eclipse in this case, because when the hotter star is the one that's behind, being blocked, that's going to be what's removing more light. So this is blue star behind red star, this is red star behind blue star. And this is, I see both of them. Is that a question?
Yeah, so
Yeah.
is the reason there's a horizontal line at the bottom of the dip, because like whether it's blocking it from here or here as it rotates, it's going to be the same?
Yeah, the reason why the bottoms are flat like that is because there's a whole extended period of time when, I'll just, here, my hand is the red star. During this whole time, the red star is blocking the same amount of area. So while the red star is completely in front of the blue star, the light is pretty much constant. As soon as the red star starts moving off of the blue star, that's when it starts to get brighter again and reaches a maximum at the moment when they are no longer blocking one another at all. So it ramps up until they're no longer blocking one another at all, is what it comes down to. Yep. Okay. Is this a question about that or something else? So, any more questions about that? Okay, you were released to ask about something else.
Could you explain the Balmer thermometer and how we use that to measure stuff like stars?
Yeah, the Balmer thermometer. Yeah, how do we measure star temperature, so to speak? Not literally measure them, but how do we tell, or why is it basically? And your book talks about this, but I think I can maybe clarify here. Gotta find the right chapter here, chapter 15. So the Balmer thermometer is the idea. So remember that stars are classified according to how strong their spectral lines are, and that all stars have essentially the same composition in that they're made almost entirely of hydrogen and helium with just a few percent of everything else. Well, Cecilia Payne-Gaposchkin, whose name was Cecilia Payne at the time because she hadn't married a fellow astronomer yet, in her PhD thesis that she wrote in the 1920s, she was the first person to show that, in fact, the differences in the strengths of spectral lines from one spectral type to another are due almost entirely to differences in temperature and not in composition. That was such an important discovery that this is widely considered to be the greatest PhD thesis ever written in astronomy, because she basically showed that most of the ordinary matter in the universe is hydrogen and helium. So that's a pretty significant accomplishment to do as a graduate student. So the idea is this. You can make similar arguments for other kinds of spectral lines, but we'll make it for hydrogen here. So I'm going to kind of tell you the story of Goldilocks and the three stars. So hydrogen lines are strongest. These absorption lines of hydrogen, those dark spectral lines, are darkest, strongest, if you will, in A-type stars, which have temperatures of around 10,000 Kelvin. At first, astronomers thought that this was because hydrogen was more abundant in some stars than other stars. But that's not what it is. It's all about the temperature. So the thing is that for the visible light spectral lines of hydrogen to be absorbed by the star, remember that the electron has to be sitting in the second orbit out, the n=2 orbit away from the nucleus, the first excited state beyond the ground state, in order to absorb wavelengths that correspond to visible light. If it absorbs photons while it's sitting in the ground state, those are ultraviolet energies, and so those are not visible light photons. But if the electron is already sitting in the first excited state, the n equals 2 orbit, then if it absorbs a photon, it will be a visible light photon. If it jumps from n equals 2 to n equals 3, the second level to third level, that's a red photon, so-called H alpha. If it jumps from 2 to 4, that's H beta, that's that turquoise colored line. If it jumps from 2 to 5 or 6, those are the indigo colored lines. So you need, for having strong hydrogen spectral lines, you need hydrogen atoms that are having the electron already sitting in the n equals 2 level. So any questions about that? That's the first ingredient. You gotta be sitting in n equals 2 to begin with. In other words, the second level there. Well, Goldilocks and the 3 stars. So Goldilocks wanted a star with nice, strong hydrogen spectral lines. So the first star she went to was too cold. And so it didn't have strong spectral lines of hydrogen. Why? Because one way to get electrons excited out of the ground state is via collisions. And remember that the temperature of a gas, or any substance for that matter, is a measure of how fast the particles are moving. In a star whose temperature is a lot less than 10,000 Kelvin, the atoms aren't moving fast enough for there to be collisions that kick the electron out of the ground state. So in low temperature stars, virtually all of the hydrogen atoms are sitting in the ground state, sitting in the lowest energy level, and they can't absorb visible light as a result. Because as I said, an electron in the ground state can only absorb ultraviolet photons. So if the star is too cold, it has weak spectral lines because virtually all the hydrogen is in the ground state. On the other hand, if the star is much hotter than 10,000 Kelvin, then the atoms are moving so fast. Chalk dust is good for coughs. The atoms are moving so fast that collisions are energetic enough to strip the electrons off of them. They become ionized. So in hot stars, then we have a situation where the collisions are so energetic, most of the hydrogen is ionized. If there's no electron, you can't absorb any photons. So in a hot star, you get weak spectral lines of hydrogen because most of the hydrogen is ionized. So Goldilocks went to a star that was too hot, and it had weak spectral lines because most of the hydrogen was ionized. But then Goldilocks went to a star with a temperature of around 10,000 Kelvin, and that star was just right. It had strong-ish hydrogen spectral lines because in that case, the temperature is high enough that collisions kick a fair number of electrons into the second level where they're ready to absorb visible light photons, but they're not so energetic that they ionize the atoms. So that's like the compromise where you get the maximum number of electrons in atoms sitting in n equals 2, hydrogen atoms. The maximum number of hydrogen atoms with electrons in the second energy level ready to absorb visible light is highest at about 10,000 Kelvin. And so that's the idea of the Balmer thermometer. In other words, you can look at the strengths of the hydrogen spectral lines and get information about how hot the star is. And if you combine that with information about lots of spectral lines for lots of elements, you can get, actually, you get a pretty precise determination of the temperature. That was a lot. Any questions? Okay. Any next questions? Yes.
How's the age of star cluster determined by looking at the main sequence?
How do we tell how old a star cluster is from looking at the main sequence on it? Yep. So, I'm going the wrong way here. So we're looking for what's called the turnoff point. And so the idea is this. Okay, so one thing to understand is that stars are born in clusters. So they're all essentially forming at the same time. They're born in litters, if you will. So stars have lots of brothers and sisters that are born in the same litter from the same interstellar cloud of gas and dust. So when we look at the stars in a cluster, they're all essentially the same age. That's fact number one. They're all about the same age because they all form together at the same time. Now, which stars live longer, spend more time on the main sequence? High mass stars or low mass stars? Which ones spend more time on the main sequence, take longer to go through all their central hydrogen fuel, nuclear fuel in their core? Low mass stars live longer, right? Because even though they don't have as much fuel, they're sippers, whereas high mass stars are guzzlers. Even though they've got more fuel, high mass stars have more fuel, they gulp it down. Their luminosity is way out of proportion to how much more massive they are, so they gulp it down. So, the idea then is, if you have a very young star cluster, you'll see the entire main sequence if you make an HR diagram for it. If you measure the spectral types or surface temperatures of its stars and measure their brightnesses, and they're all the same distance from us because the cluster is much smaller than the distance to us. So you can just plot their brightnesses, and that'll be, since they're all the same distance away, you don't have to worry about the fact that they could be at different distances, making the apparent brightness differ from the luminosity. A star which is more luminous looks brighter in a cluster because they're all the same distance from us, essentially. So a young cluster, you can see the main sequence all the way up to the O-type stars. Everybody's there, so to speak. It's a little more subtle than that because low mass stars take longer to form, so you can actually get a situation where the low mass stars haven't even gotten to the main sequence yet. But let's not worry about that complication. Now, imagine that you came back a few million years later and plotted the HR diagram of the same cluster. The idea is that the highest mass stars will have already run through their central fuel by then and leave the main sequence. When a star, as we'll see when we talk more about stellar evolution, stellar lives, when a star runs out of central hydrogen fuel, it's no longer on the main sequence. It moves off of the main sequence on the HR diagram. So, if you come back in a few million years, the upper part of the main sequence is missing because those very massive stars already went through all their fuel. Come back millions of years later, and now these stars have left the main sequence because they went through all their fuel. Come back later, more and more stars have left the main sequence because they've run out of their central hydrogen fuel. So what we can do is say, okay, the lower down you are along the main sequence before there are no more stars on it on the cluster's HR diagram, the older that cluster must be because the more massive stars than that have already left the main sequence. And so what you do is you find out the spectral type of stars at the so-called turn-off point, where stars are just now leaving the main sequence, at the top of its main sequence. You find the spectral type of those stars. Computer models tell us how long stars of that spectral type will spend on the main sequence. So if you look at a cluster and find, for example, that stars of spectral type G are just now leaving the main sequence, then you would be able to tell that that cluster was about 10 billion years old because stars of spectral type G spend about 10 billion years on the main sequence before they run out of fuel. And so that's what it comes down to. What you do is you find out where the turnoff point is, and computer models tell you how long it would take a cluster to get to the point where that's where its turnoff point was. It's a little more sophisticated than that in that we actually do what's called main sequence fitting, where you can actually plot what the HR diagram of a cluster of various ages should look like, and you overlay that on the cluster's HR diagram for various predictions of what the HR diagram should look like for various ages and find the one that best fits, is what it comes down to. But in a nutshell, where stars are turning off the main sequence tells you how old the cluster is. So if I've got two clusters, and for one of them, it does not have O or B type stars on the main sequence. So one cluster has no O and B type stars. Another one not only doesn't have O and B type stars, it also doesn't have A type stars as well. Which of those two clusters is older? The one that's missing O and B from the main sequence, or the one that's missing O, B, and A from the main sequence? Which one's older? O, B, and A. O, B, and A. The further down the main sequence stars are missing, the older the cluster is, because it's had time for lower and lower mass stars to have burned through their central hydrogen store of fuel and no longer be main sequence stars. So you can tell qualitatively, you can compare the ages of clusters by figuring out which one has a lower down on the main sequence turnoff point, and that one's always going to be older than the one that has a higher up place on the main sequence where the main sequence stops, because all the more massive stars than that are not on the main sequence anymore, they're gone. So, any questions about that? And of course, could you repeat something is always a good, not question, but statement. That's always a totally legitimate statement. All right, yes?
So, say that the main sequence is stopping at G, you would use a computer model to see how long G stars typically live for, and that's all of the cluster.
That's right, yes. If the main sequence stops at G, if it's got M stars and K stars and G stars, but nothing beyond that, we have sophisticated computer models that predict how long G stars live. We can even do better than that. We can say if the turnoff is at G4, you know, in other words, remember that each spectral class is subdivided into subclasses. If the turnoff point is at like G4, we can even say from our models how long do G4 stars live on the main sequence. But yeah, that's the idea. Computer models tell you how long stars of various spectral types on the main sequence will spend on the main sequence. Where the turnoff point is, how long those types of stars spend on the main sequence is how old the cluster is. Because it's lived long enough that those stars are just now running out of central hydrogen fuel. And then you might say, well, how do we know those computer models are right? And that's because it works both ways. In other words, the computer models predict what HR diagrams of clusters should look like. And as we talk about stellar evolution, you'll see that they do a beautiful job of reproducing. So we have great confidence in our computer models because they do such a good job of predicting what star cluster HR diagrams ought to look like, theoretically, and then we confirm that observationally. Yes?
What's the importance of the arc minute and arc second?
Of arc minutes and arc seconds?
Yeah, is it just where you can tell where things are in relation to others, or how big they are?
It's so you're asking about arc minutes versus arc seconds and so forth.
Yeah.
Those are angles, right? Those are measures of angles. And so when we look at things on the sky, we can't directly tell how far apart they are in space from one another. All we can tell is what's the angle between them on the sky. Now, under the right circumstances, if we know how far away something is, knowing that angle also tells us how big it is. So the angle, if we know the distance, the angle can also tell us how big things are. But sometimes we're just wanting to know the angle between them for relative information, like in other words, how big two orbits are relative to one another. If we don't know the distance, that's the best we can do. But the importance of those angle measures is that's what we can directly measure on the sky is angles between things, because we can't see how far away they are. Yes?
Could you go over the model that we drew in class about how atoms fuse in the sun?
So you're talking about, yeah, so like the proton shape, in other words? Right. Yeah, so remember, you can get some extra credit for memorizing the proton-proton chain. It's worth 3 points extra credit if you do that, so that could be worth it. Now, would it be the thing I do instead of being sure I understand everything else? No. But if you get to the point where you're happy with your knowledge of everything else, then you too could decide, yep, I want to draw this lovely picture right here. Actually, I would be satisfied if you just drew the top half of it up to here and said, and by the way, this gets repeated down there. So in other words, the steps are, first thing is 2 protons, 1 H is a proton because it means hydrogen, which is a proton. Hydrogen has 1 proton in the nucleus, so a bare proton is a hydrogen nucleus. The 1 means there's only 1 particle in the nucleus. Hydrogen means that 1 particle is a proton. 2 protons collide and make a deuterium nucleus, which is still hydrogen because it's only got 1 proton. And it's only got 1 proton because one of the protons turns into a neutron by spitting out a neutrino and a positron. And then the deuterium smacks into another proton and forms helium-3, 2 protons and a neutron, and it spits out a gamma ray as well because it's formed in an excited state, and then when the nucleus drops down to its ground state, it's not electrons that are doing it, it's the nuclear particles that are doing that. When they drop down to their lowest energy level, they spit out a gamma ray when they lose that energy. And then 2 helium-3s, which were both formed in exactly the same way, 2 helium-3s fuse with one another, 2 of the protons get spit out again, and 2 of them stick around in the helium-4 nucleus, which is the final product here. So notice that the 2 helium-3s have 1, 2, 3, 4 protons between them. Only 2 of them stick around in the helium-4, the other 2 are spit out again. So if you can draw this picture, that's 3 points of extra. Draw and label the picture, that's 3 points of extra credit. Again, what I want you to definitely know is the overall reaction, which is that 4 hydrogens form a helium-4 plus energy. 4 hydrogens because even though 1, 2, 3, 4, 5, 6 of them go in, 2 of them get spit back out again. So on the whole, 4 hydrogens make 1 helium-4 plus energy is the fusion reaction in the sun. But extra credit if you memorize the details because, I mean, who wouldn't want to know all the steps of the proton-proton chain, right? Right. So. Certainly a way to impress the relatives. All of your questions have been answered.
I was gonna go home, it's pretty late.
Yeah.
It's a long drive, 40 minutes, so.
Oh, okay, yeah, well, drive well, I guess.
Have fun going.
Could you go through
Interferometry.
I know what it is, I don't understand how it actually functions.
Yeah, you know, the thing is, honestly, in a class at this level, it's hard enough to teach a graduate student how interferometry works. It's actually pretty subtle. So for our purposes here, I just want you, you have to, basically it involves taking the inverse Fourier transform of the visibility function as deduced by the set of interferometers and their various baselines and angles between one another. I'm sure that was all very enlightening. So what I want you to understand is the basic idea here. Let's see, was I smart enough to put a picture of interferometer? I may not even put an array in here, it's just in the book. But the idea is that, remember that angular resolution depends on the diameter of the mirror or the lens in a telescope. The bigger the lens or the mirror, the better is the angular resolution. Remember that the wave nature of light limits how sharp we can make images. It's why images are not perfect little pinpoints. And the bigger the lens or the mirror is, the smaller is the images of the stars that you make, the finer the details, the images you can make. It's possible to electrically combine the signals of radio telescopes, and now even it's becoming to be possible to do this with infrared telescopes too, and maybe even visible and even visible light. But by combining the signals of radio telescopes separated from one another, it turns out you can use that to get an angular resolution which is the same as you would get if you had a giant radio telescope whose size was equal to the distance between the radio telescopes. And that's what I want you to understand, is that by linking radio telescopes together that are widely separated from one another, you can get an angular resolution which is good as you would get if you had this giant radio telescope that was the diameter, whose diameter was equal to the distance between the radio telescopes. So for example, we have linked telescopes on opposite sides of the Earth to get extremely high resolution radio images, radio wave images, comparable to what you would get if you had a radio telescope the size of the entire planet Earth. And it's called interferometry because it uses the way that waves overlap and add and subtract one another from one another, and that's called interference with one another. So it's interferometry, in other words, measurement using interference of the radio signals coming to the two telescopes or more telescopes. Yes?
Could you explain why the sun's luminosity gets stronger over time?
Yeah, why is the sun getting slowly brighter over time? The reason for that is that, remember, that every time you fuse hydrogens to make a helium nucleus, you're starting with 4 particles. Yeah, I'm trying to, let's see what I do with that piece of chalk. Yeah. So the overall reaction is that 4 protons forms 1 helium nucleus. 4 protons forms 1 helium nucleus. So the number of particles in the sun's core is going down as a result of fusion. Number of particles in the sun's core is decreasing with time. Now, turns out that pressure equals number of particles per cubic meter times what's called the Boltzmann constant times the temperature. This is one way of writing the so-called ideal gas law. If you ever took chemistry, you put it in terms of moles and so forth. But this is an equivalent way to write it. It's the number of particles per cubic meter times a number called the Boltzmann constant times the temperature in Kelvin. So here's the deal. Let's call this N like we usually do. N times K times T. The pressure is what's called the number density, number of particles per cubic meter, times this Boltzmann constant times the temperature. The pressure has to support the weight of the layers above. It has to support the weight of the sun's outer layers. Well, that's not really changing. They're just still there. So N is decreasing. If I keep having to exert the same amount of pressure, essentially, what has to happen to the temperature? If N is going down, and NKT is how much pressure there is. If N is going down, what does T have to do to compensate? T has to go up. compensate. What's really happening is that there's not quite enough pressure to hold up the outer layers, and so the sun's core is actually very slowly contracting and turning gravitational energy into thermal energy. That's the mechanism by which the temperature is increasing. And here's the deal. Remember that nuclear fusion requires high temperatures. Things have to be moving fast enough to overcome their electrical repulsion. So if the temperature is increasing, what's that going to do to the rate of the nuclear reactions? It's going to speed it up. So in other words, the slow increase in the sun's core temperature is actually speeding up the nuclear reactions. And by that energy balance, it says that for the sun to be stable, the amount of light it's emitting from its surface has to equal the rate at which it's generating energy in its core. The sun's luminosity has to be increasing with time as a result of that. And in fact, eventually that's going to turn the Earth into another Venus, because eventually the sun's luminosity will be high enough that it will drive the Earth into what's called a runaway greenhouse effect. It will evaporate, it will make the oceans start evaporating, and that'll set us on a cycle that turns us into more of a twin of the planet Venus, where we have a really extreme runaway greenhouse effect with a really thick carbon dioxide atmosphere and so forth. That'll be in about 500 million to 1 billion years or so it's not something we have to lose sleep over. But it's interesting that the sun will toast the Earth long before the sun swells up and becomes a red giant after it runs out of central hydrogen fuel. This will happen while the sun is still a main sequence star. So our distant descendants will have needed to go somewhere else by then. Or we could put a giant parasol between us and the sun at what's called the L1 Lagrangian point. Fun fact.
Should we know the formula, or do we just need to know the concept?
Just know this concept that as the number of particles goes down, the temperature has to increase to keep the pressure high enough, and that's making the nuclear reactions go faster as a result of that.
Good, thank you.
Yep. Really like we need a good night's sleep.
Yeah,
Yeah.
that did not occur this week.
Oh, really? I hope it's because you were having too much fun.
I was having fun.
Yeah, okay. At least there's that. Yes?
Can you talk about the photosphere in terms of like the sun's visual appearance?
Yeah, so, when we take photographs of the sun, or, and don't do this much, when you just look at the sun with your naked eye, it looks like it's a solid ball, right? It looks solid. And in fact, the sun is really a big ball of gas. It doesn't have a solid surface, even though it looks like it has a solid surface. Well, what our eyes perceive to be the surface of the sun, what looks like the surface of the sun, that is the photosphere. The photosphere is a layer that is only about 400 kilometers thick. That is where most of the visible light scatters off of something before escaping out into space. And so as a result of that, most of the visible light photons we see from the sun came from that layer that's about 400 kilometers thick. Well, 400 kilometers sounds like a lot. It's about 250 miles or something like that. But you have to remember that the sun is almost 1 million miles across. So 250 miles out of 1 million miles is almost nothing. So as a result, the layer of the sun from which we get most of the light is so thin compared to the size of the sun that if you take a piece of, if you like, I'm going to draw the sun, and you do it by taking out a pencil and drawing a circle, the thickness of that pencil line compared to the circle that you drew is way thicker than the photosphere is compared to the size of the sun. So compared to the size of the sun, we're seeing the light coming from a very thin layer, which gives us the illusion that it's coming from a solid surface, even though the sun is entirely made of gas. And that layer is called the photosphere. It's what we literally see with our eyes, unless we stare at it too long and then we stop being able to see things, but don't do that. You're welcome. Yes.
We touched on this in class, but can you go over again why we place really big telescopes on mountaintops?
Yeah, why do we do this? Why do we put telescopes on mountaintops? Of course, my smart aleck answer, or your smart aleck answer, if you wanted me to cry, would be to get them closer to the stars. Of course, you're not actually supposed to say wrong answers because, you know, psychology studies where say something wrong to people and they remember it and they think it's right, you know, even if you know it's wrong. But I think my histrionics about how much I'll cry if you say it's to get them close to the stars to get people to realize, no, that's not it. So one thing it does is the air's thinner up there, right? You're above most of the atmosphere. And that's really what it comes down to. You're trying, because remember, astronomers have a love-hate relationship with the atmosphere. We appreciate the oxygen, but other than that, the atmosphere messes with our observations. Atmospheric turbulence causes stars to twinkle. It blurs images. Water vapor in the atmosphere absorbs infrared light very effectively. It's why water vapor is a good greenhouse gas, as they call them. Water vapor is the primary greenhouse gas in Earth's atmosphere. And so getting above as much atmosphere as possible gets us above the blurring effects of the atmosphere, the dimming effects of the atmosphere, because there's not as much dust up there. Dust in the atmosphere blurs, dims starlight before it reaches the ground. So in other words, it's not to get them closer to the stars per se, it's just to get them closer to being above the atmosphere, even though there's still plenty of atmosphere above even the tallest mountaintops. Of course, the ultimate goal then, to really get above the atmosphere, is you put the telescope in space, yeah. But that's a lot more expensive than locating it on a mountaintop. So, and you know, I mean, put a giant telescope in space, it's a lot harder to maintain it than if it is on the ground, for example.
So we need to know which ones you can see on the ground and which ones have to be up into space.
For like which types of light and so forth. Yeah, you should know that. There's a good section in the Mastering Astronomy about that goes through all of that. But really what it comes down to, it's actually fairly simple. We can see visible light and radio waves on the ground, and pretty much nothing else. I say pretty much because we can see some near ultraviolet, in other words, ultraviolet wavelengths that are not too much beyond the visible part. We can see on mountaintops, and well, even on the ground, even like here, we can see some infrared light that is almost at the visible part of the spectrum. So like at Perkins Observatory, I take infrared images, but it's very near infrared. It's wavelengths that are just a little bit longer than red light is. But to an awfully good approximation, what it comes down to is, if you want to see anything other than visible and radio, then you should be in space. Or with some infrared wavelengths of interest, you can do it from aircraft, or a little bit at high mountaintops and stuff like that. That's what it comes down to. And then a little bit of ultraviolet and infrared even at sea level, but that's the main thing is there's a visible so-called window and a radio window where the air is transparent, and pretty much anything else you should be in space or in an airplane if you're talking about infrared. That's kind of the quick summary. Is that acceptable? Yep. You haven't asked anything. We'll just throw something out there.
So if you put a telescope in the space, but when you look at star, you look at the night, right?
When you look at star at night, you said?
Yeah, usually on the surface, you look
Right.
at night.
Yeah.
So if you put the thing in space, would the lights come directly to the?
So the thing is that if you are in space, you know, the reason why we have to look at night on Earth is because during the day, the air scatters lots and lots of sunlight and makes the sky blue. And it completely blasts away our ability to see stars during the day other than the sun, because the bright blue sky drowns them out completely. But in space, you don't have that problem. And so as long as you are shielding the mirror from direct sunlight, you're keeping direct sunlight from hitting it, and you're not pointing it at the sun, then the sky looks black, full of stars, when you're in orbit around here. So the Hubble Space Telescope just has to not point in the direction of the sun, is what it comes down to. And in those directions, the sky is black. And plus, you know, when if you're on the night side of Earth, if you're in part of the orbit where you're in Earth's shadow, even better. Then, yeah, it's dark. You know, you don't have to worry about sunlight there, and you're above all of the Earth's atmosphere. So typically, you know, telescopes in space will observe when they're on the night side of their orbit around the Earth. It's easier than when they're on the day side. But you can, you know, under the right conditions, you can also observe on the day side as long as you're shielding the optics from the direct sunlight, which you can do. Yes?
On your study guide, I'm not even sure what it means. What force binds atomic nuclei together?
Oh, that is that's in the book. We didn't mention it, I think we mentioned it in class briefly, but the strong nuclear force. Yeah, we did mention that in class. So your book describes it. So the strong, there's four forces of nature. There's the strong nuclear force, there's the weak nuclear force, the electromagnetic force, and gravity. Those are the four forces of nature. And the strong nuclear force is, as the name kind of implies, the strongest of them, but it's also very short range. So two protons, or a proton and a neutron, or two neutrons will attract one another via the strong nuclear force, but only if they're practically touching one another. So the reason why fusion requires high temperatures is that they have to be moving fast enough to overcome their electrical repulsion and get close enough to feel their strong nuclear force attraction for one another. And the analogy your book makes is that the strong nuclear force is kind of like Velcro. Velcro only exerts an attractive force when the things are essentially on top of one another. And for the nuclear particles, the strong nuclear force is like that. They have to be virtually on top of one another for the strong nuclear force to kick in and attract them to one another. You're welcome.
lecture tutorials, we have a small hot plate that's very hot, and then we have a big one that is,
Not as hot.
yeah.
Right.
You can't tell the difference.
Right, you would have to know the actual temperatures and the actual sizes and calculate how much power each one was putting out. Without detailed information, you cannot know which one is going to cook the spaghetti faster, which one is giving off more power. Because you've basically got things working in two directions. In other words, if your goal is cook spaghetti, big helps you and hot helps you. And in that case, one of them's got big going for it, and the other one's got hot going for it. As opposed to the other ones they have there, where if I've got two of them at the same temperature, the bigger one wins, right? If I have two that are the same size, the hotter one wins. It's not ambiguous there. But if I've got a small hot one and a big cool one, then each of them's got something going for it and something going against it, and so then you need a detailed calculation.
Thank you.
You're welcome.